In this recording, I will attempt to demonstrate what's meant by downhill when we talk of electrical potential. Okay, for that, I'm going to use a simulation from this website by Falstad. Now, what I'm going to show you, the simulation allows a diversity of configurations, but I'm going to show you this particular configuration where we have two equal charges, one positive and one negative, that we are going to place. So we call that a dipole usually. A dipole is made up of two equal charges, one positive and one negative. The color in the simulation is going to represent the strength of the electrical potential. Green would be positive electrical potential and red is negative. So here we are seeing green, here we are seeing red. Gray would be zero electrical potential. And the surface, what you are looking at here, would represent the electrical potential. For example, if I'm getting up here, I'm going uphill to a higher and higher electrical potential. And here I'm going downhill into a sort of a well, of increasing electrical potential in the negative direction, of course. The white dots that you see here are small positive charges. When we say small, what we mean, they are so small not to affect the overall electrical potential that we see here. Remember, each charge is going to have its own electrical potential, and the overall electrical potential is the electrical potential due to all charges. However, if these main charges are so large compared to these, the effect of the tiny positive charges is going to be too small to notice. Okay, let's go to the simulation. Here is the simulation. And you notice, actually it allows us to look at this in a little bit 3D. You see the white positive charges are looking like they are falling deep into this well. Let me increase the number of these charges, and they are falling down from this big mountain. The height of the mountain determines the strength of my electrical field. Now you notice as we get closer to the charge, we don't see a tip here, because as we get closer to the charge, it gets larger and larger. It depends on 1 over r. So the smaller r, the larger it gets, so it borders infinity in the middle. So that's why we're not seeing that. And then the opposite here, it's a well instead of a mountain, because we have a negative potential. And you notice here, in between, we have a zero electrical potential, and we have zero electrical potential, or close to zero electrical potential somewhere here. Remember, these are equipotential lines. These are lines of the same electrical potential, like topographical lines. Okay, let me stop this one. Now the other look is this one here. So it's the same two charges, again an electrical dipole. We're not going to see the three-dimensional relief, but we are going to look at it in 3 dimensions. Now, it sounds a little contradictory, but here these surfaces are just a way to visualize what's happening. But in real life, this is what we have. This is the electrical field. Let's look at it. So this is the electrical field, and what we are looking at is a slice. This is very much like they do MRIs, for example. And then if I would like to look at the electrical field a little bit ahead of the charges, actually I was looking in behind, so this is what we get. We don't see anything. So here you see the equipotential lines change as we get closer to the charge, and then now we go behind the charges. Okay, this is we are looking at what they call a Y slice. Now I can move this around. So this is where our charges are, and this is when I see the pattern we were talking about. But if I'm moving away from the pattern, since it's three-dimensional, you're going to see that effect. Now, if I ask, for example, for an X slice, so on that slice, it's going to look more circular. Okay, if Z slice, okay, that's going to be very much like the Y slice, but in the Z direction. Now, if we don't want to slice it and try to have an overall look, it's not going to be as fun, but we can see it. Okay, let's see how many of these can we have. I'm not sure. Okay, so in this case, what this is allowing us, what if we go to looking for negative potential, so we find it close to the negative charge, and then here zero potential, and then we are going for the positive potential, so get to the positive charge. And remember, it is spherical in shape close to the charge, but then the dimensions get a little bit more complicated. You see it here. It's not really spherical because I have the positive charge here. Okay, and see the shape. Now, I'll show you for a second what we would get if we have only 1 point charge. And again, no slicing. So we should see just a spherical shape. That's our equipotential surfaces are spherical in shape. Now, if we have two identical charges instead of two opposite charges, then the electrical potential has this kind of shape. The equipotential surfaces take this kind of shape. And actually, let's go back to this other simulation. And look at it. Unfortunately, it's a different browser. Okay, so let's look at two identical charges. The color showing us the potential. See here, it's a negative. Okay, and you notice here let's reverse the charge. You notice here we have the big potential, and then the surface, the equipotential surfaces are somewhat like this.